तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
So, this will be lecture number 15, mechanical measurements. In the previous lecture, we were looking at the errors in measurement of temperature under various circumstances. Now, we are going to look at the measurement of temperatures which vary with time. So, these are called temperature transients, or measurement of temperature which varies with respect to time. What we will be doing in this lecture is to look at a temperature sensor and describe it mathematically in terms of a first order system behavior, and we will also draw an analogy with electrical circuit theory, and we will look at the similarities between the two systems. We will look at the governing equation, we will derive it and then work out what we call as the general response for any variation of the temperature, and after doing that I am going to take 3 particular cases. The first one will be response of the sensor to a step input or step change in temperature. It will become more clear when we look into the details. Then response to a ramp input where the temperature is varying linearly with respect to time, and response to a periodic input, a pure sinusoidal or pure cosinusoidal variation of the temperature with respect to time, and we will see what is the reason why we do that as we go along, and then we will also look at a few representative cases and consider one example and work it out on the board. The basic model which we are going to use for describing a temperature sensor is in terms of a lumped thermal system, which is schematically shown in the slide here. We have an object, the sensor is supposed to be represented by this object which is shown here. Of course, the shape and size and other things will come later on. We will assume that at any time t, the entire sensor which is represented by this irregular shaped body here is at a temperature T which is same throughout. It is a homogeneous temperature field within the sensor. We will also characterize the sensor by a characteristic dimension, we call it L subscript CH, which is the characteristic dimension as far as the geometric variables describing the body is concerned. The characteristic dimension is what is going to come in the description of the thermal behavior of the system. We also visualize a fluid stream which is at a temperature equal to T infinity, which may of course be varying with respect to time, and it subjects the sensor at its surface to a heat transfer coefficient H watts per square meter degree Celsius. There are several different ways of looking at it. For example, if the temperature is the same, T infinity is constant, and initially the body is at a temperature different from the temperature of the fluid, and let us say we turn on the heat transfer coefficient by turning on a fan, for example, or some method by which the flow takes place, then immediately the temperature of the system starts changing. Another way of visualizing the problem is, suppose the temperature T infinity is one value to start with, and suddenly there is some mechanism by which I change it. I want to find out what happens to the temperature indicated by sensor. It will be ideal if the sensor follows exactly what is happening to the temperature of the surroundings, which it is supposed to be measuring. Invariably there will be a difference between the temperature indicated at any particular time by the sensor as compared to temperature of the ambient whose temperature I want to measure. Therefore, we expect a difference between the indicated temperature or the temperature of the body sensor at T at a particular time T. This will be different from this temperature. So, the idea is to look at what are the differences, how they depend on the various parameters which govern the problem, and for doing that I have given a slightly different schematic here. I have a sensor idealized as a spherical object here. It may be visualized as a spherical shell, and I have introduced a thermometer or a temperature sensor somewhere in the shell, and because we are assuming that the shell is entirely at a uniform temperature at any given time, there is no variation of temperature within the shell, the thermocouple position in the shell is of no significance. We will also assume that the lead wires are very, very thin, so that there is no heat loss due to the lead wires which are attached to it. Of course, if the lead wires are going to conduct significantly, then we will have to take into account. That is not very difficult, but it becomes a little more difficult too in terms of the description of the problem. We will assume that the shell, which is a spherical shaped object here, is characterized by a mass of m. It has got a surface area which is in contact with the ambient fluid which is flowing across over the surface of capital S, and it has got a specific heat capacity of C. The units will be mass is kg, S is square meters, and C will be joules per kilogram Kelvin. And the ambient fluid is going to subject the surface to a heat transfer coefficient H, watts per square meter Kelvin, or watts per meter squared degree Celsius, and the temperature T infinity is the ambient fluid temperature, which may be either stationary, that is constant, or it may be varying with respect to time in a particular fashion. It may be even periodic. So, we are interested in 3 different cases where the temperature is in fact constant and the initial temperature of the sensor is different from that temperature. It may be either higher or lower. The second case where the temperature T infinity is actually varying with respect to time in a linear fashion, which is normally what happens if you start heating for example an oven which is in the off position. You turn it on, initially the heat is input to the system and the temperature is likely to vary in a linear fashion. Or you may set up an experiment where you want to specifically heat an object at a constant rate of temperature increase with respect to time. So, then I would like to follow the temperature as it changes for that particular experimental purpose. The third case is where the temperature is actually varying periodically with respect to time, cyclically in a fashion in terms of a sinusoidal variation, and then I would like to find out how the system is actually the thermometer here, how it is going to respond to the changes or the variations in T infinity. We will see in a moment. I will work it out on the board. The thermal capacity of the system is the product of mass and the specific heat, which is important. Mass times the specific heat, that is m into C. So, C is joules per kilogram Kelvin and m is kilogram, therefore, it becomes joules per Kelvin, that is the unit of thermal capacity. And then you have the thermal resistance, which is nothing but 1 over the heat transfer coefficient surface area product. And again you will notice that 1 over Hs is units of resistance. This will be in Kelvin per watt, that will be the unit of that. So, the first order system, which I have not yet defined in terms of an equation, which I will do in a little while from now, is defined by the quantities which are shown in this figure, and the mass specific heat product is going to be one of the important parameters, and the second parameter is going to be the resistance to heat transfer from the surface, which is given by 1 over heat transfer coefficient area product. So, with this background, let me go to the board and look at the system from a thermal point of view. So, we will consider the thermal model. So, I will just indicate the sensor and we have already seen that mass and specific heat and the surface area is S and the heat transfer coefficient and T infinity are given. To be more specific, I will say that the T infinity is possibly a temperature function of temperature. Okay. Therefore, and let us assume that initially at T equal to 0, T of the system will be indicated by T subscript I. So, let us look at the way the temperature of the sensor is going to vary. So, this is your T subscript C at T throughout. I am assuming that it is uniformly the same temperature throughout that object. Let us look at the rate of change of the temperature of the system. Suppose if we say that T at any instant t is not equal to T infinity at that particular instant of time, there will be heat transfer in this direction. Of course, depending on which temperature is higher, the heat transfer direction will depend on the direction of decreasing temperature. It will be in the direction of decreasing temperature. So, let us look at the way we are going to model this. So, the change in the internal energy of the sensor if it is going to lose heat, if we are going to lose heat, that means if the temperature at any instant of the sensor is greater than the temperature of the ambient, when it loses heat, the temperature will reduce. Okay. So, the rate at which the internal energy is changing or decreasing is given by mass into specific heat. I am assuming that all these are constant, are not varying with respect to temperature, dt by dt. This is the rate at which the heat transfer, the internal energy of the system is changing, and the heat loss or heat loss from the from sensor, that will be sensor to ambient, whose temperature is what I am trying to follow, is given by H into S and to T minus T infinity. Both are of course functions of time. I am not showing specifically here, and it is understood that both temperatures T and T infinity are essentially functions of time. So, if the heat loss is from the sensor, that is the heat is going in this direction, the temperature of the sensor is going to reduce. Therefore, dt by dt is negative, dt by dt is negative. Therefore, if I take negative of this mc dt by dt, that will be equal to the heat loss. That is how you write the equation. So, the conservation of energy requires conservation of energy requires that the change in internal energy, which is minus mc dt by dt, must be equal to Hs into T minus T infinity. This equation is valid whether T is greater than T infinity or T infinity is greater than T, because automatically the sign of dt by dt will change to accommodate these changes. Therefore, when I derive the equation, assume that the temperature of sensor is greater than the temperature of the ambient, so that I derive the equation with that assumption. But in a case where the temperature of the sensor is actually smaller or lower than the temperature of the ambient, both the left hand side and the right hand side will change their sign, and therefore, there is no change in the equation. So, this equation can be rewritten in the following form. So, what I will do is I will remove this mc from here, I will take it to the denominator, and look at this mc by Hs. this is the mass specific heat product. Let us look at the unit of this quantity. This will be kilogram, this will be joules per kilogram Kelvin, divided by H is watts per square meter Kelvin. So, watts is nothing but joules per second into 1 over meter squared Kelvin, and this is meter squared. So, you see that this meter squared will cancel off with this, Kelvin will cancel off with this, kg will cancel off with this kg, joules will cancel. So, this becomes unit is second. So, this MC by Hs has the units of second. Usually it is written as tau, and we call this the time constant of the system. Time constant of the first order system. Why is it first order system? Because the equation has a first order derivative in the equation. It is governed by a first order equation. So, with this notation MC by Hs equal to tau, I can rewrite the equation very simply as dt by dt plus T by tau is equal to T infinity divided by tau. This is the equation governing the problem. So, the first derivative with the temperature of the system or the thermometer with respect to time plus T by tau equal to T infinity by tau, and we will recapture, we will reaffirm that T infinity could be a function of time. So, if you want, you can indicate here explicitly that it is a function of time. It could be different function, and also we know that the temperature of the sensor is initially T0 is equal to Ti. So, we have the equation governing the problem, which is the first order differential equation, ordinary differential equation, with the initial temperature given as T at T equal to 0 equal to Ti. So, solution of this is essentially what we are going to look for. So, before we proceed with the solution, let us look at some other details, and the details I am looking at essentially is the quantity tau, which we have just now seen that it is nothing but MC divided by Hs, and MC is like the, if I look at the electrical analogy or analog, MC is like the capacitance and 1 over Hs is like a resistance. And you see that if I show it as capital C and that as R, the time constant for a electrical system is R times C, and exactly that is what we have here. If you want, you can show it as 1 over H is the thermal resistance. So, I can say it is R thermal, and C MC is actually the C thermal. Okay, tau is equal to. So, this is the analogy between the two systems, that is number 1. Number 2, the time constant is dependent directly on the mass specific heat product. So, the larger the mass or larger the specific heat, the time constant is larger, and the larger the resistance, that means that Hs product, the smaller the value of heat transfer coefficient surface area product, the larger the time constant. And in fact, I can rewrite this MC by Hs slightly in a different fashion. M is also equal to rho times the volume of the sensor. So, rho is the density and V is the volume. So, if I do that, then I can write tau as M is rho into V, I will write rho C multiplied by V divided by H into divided by S. So, I am dividing it into two groups two groups. This first group is thermal in origin, and this is geometrical, which has to do something with the size and the shape of the sensor. So, it is actually the volume to surface area ratio. So, now you can see that if I make the volume to surface area ratio as small as possible, or I reduce it, I will be able to get a smaller time constant. And we will see in a few minutes from now that a smaller time constant is better if you want to follow the changes as accurately as possible, as closely as possible. Therefore, the control I have over how a temperature sensor is going to respond, there are two factors which I can vary, or I can choose, or I can manipulate. The geometrical one is very easy to manipulate, because all I have to do is to see that V by S is as small as possible. Suppose I take the following example I can take. Suppose I take a sensor in the form of a spherical shell. So, that is, let us say R, and the thickness is delta. This is a spherical shell. So, we can see that volume is equal to 4 pi r squared delta, and the surface area is 4 pi r squared. So, the volume to surface ratio, area ratio, is nothing but the is equal to delta. In fact, we will be referring to this as the characteristic length. So, if I have the sensor attached to a small spherical shell, what is the advantage I am going to have? I am going to have a very small characteristic length, and this characteristic length being small, it means that it is going to reduce the time constant of the system. Therefore, instead of taking a spherical solid object, if I take the object in the form of a spherical shell, I will be able to reduce the time constant, because the characteristic length is going to reduce. Okay. However, if you look at the heat transfer point of view, I can choose a very large value of R, so that it is a large enough object, so that the heat transfer can be improved by having a good heat transfer coefficient in this particular case. So, you can see that there are several things which are manipulated at the same time by this technique of taking a spherical shell object. In fact, I can also take the object in the form of a thin film of very small thickness like this. It has got two surfaces, one on the this side and the one on the right side. That is, the total area is the two surface areas, and the volume is the surface area multiplied by small thickness. So, again the thickness, if it is delta, the characteristic dimension becomes exactly equal to actually equal to delta by 2. So, I will say LCH equal to, because there are two surface areas and the volume is proportional to surface area multiplied with thickness, therefore, I get a delta. That means that the time constant can be manipulated by simple geometric arrangement, where I am going to take the sensor in the form of a thin shell or in the form of a thin film, and this thin film can be very thin. It could be a few micrometers in thickness, and it could be very large surface area, maybe a few millimeters width and a few millimeters height. So, this is one part of the description of the system. I have not solved any problem, I have not solved any equation, but by just looking at the equation I am able to get some insight into the thermal behavior of the system. With this background, let us look at the governing equation which was derived on the board, and I have written it in this slide. just to recapitulate, what I have is the change in temperature with respect to time, dt by dt is the rate at which it is changing, is given by a difference between temperature of the ambient, which may be varying with respect to time, minus the temperature T, which is the temperature of the sensor, divided by the tau, which is the time constant. So, dt by dt equal to T infinity minus T divided by tau. This is the temperature difference, or it is like the voltage potential difference, and divided by time constant is something like a characteristic time for the particular problem, and which is given by MC by Hs. And in the next slide, I am showing the electrical analog of the same situation. The time constant system is RC, where R is the resistance and C is the capacitance, and suppose I connect the resistance and capacitance like this. I input a voltage V in, this is like the T infinity, and the output voltage V out is the response of the system. So, R C in series like this, and I am putting the input as I shown here. This input may be either constant or varying with respect to time, and then the output is going to appear across the object, which is the system capacity, heat capacity. Actually, you can see that the resistance which is in series with the capacitance is something which connects the output, which is what we want from this system, the temperature of the object, to the temperature variation on the outside. This is something like an interaction. The resistance allows an interaction between the ambient and the system, and the system itself is characterized by the capacitance C of the system. So, the relationship between V out and V in is what we are going to study, and let us look at the way we are going to do that by again going back to the board, and let me just try to work out the so called general solution to the problem, which is very simple. So, general solution to the first order equation. So, we know that it is dt by dt plus T by tau is equal to T infinity, which is a function of time divided by tau. Suppose I multiply throughout by e to the power of T by tau, which is an integrating factor. So, if I multiply these two, the left hand side becomes e to the power of T by tau dt by dt plus e to the power of T by tau multiplied by T by tau is nothing but d by dt of e to the power of T by tau multiplied by T. You can verify that. So, the right hand side is equal to then T infinity by tau multiplied by e to the power of T by tau, and all I have to do is to integrate it once. If I integrate, I will get e to the power of T by tau multiplied by T is equal to some constant of integration. I will say it is A plus 1 over tau, it is a tau is a constant, I will just take it outside, integral 0 to T infinity, which is a function of given function of time e to the power of T by tau dt. And in fact, you can see that the integral shown here for t equal to 0, the upper limit and the lower limit will be the same. Therefore, and this will become 1, e to the power of 0 by tau becomes 1. Therefore, A is nothing but T I, and therefore, I can write the solution as T, which is a function of T. I will multiply throughout by e to the power of minus T by tau. So, that become T I e to the power of minus T by tau plus e to the power of minus T by tau divided by tau integral 0 to T infinity dt. This is the general solution, and in fact, I can use this as the starting point to write down the solutions for all the 3 different cases we are going to consider. The 3 different cases, if you recall, one will be a step input. I will explain this using the electrical analogy. You have resistance and then you have the capacitance, and you are going to connect it with a, and you are going to measure the output here. So, in this case, initially I do not have any input, I just give an voltage at the input by turning on a switch, and you have, let us say you have a battery and then you connect it. So, what initially will happen is, from the battery current will flow through the circuit, and this current flow will be taking place till the capacitance gets charged. Once it gets charged completely, the current will stop. Okay. So, there is the transient. The transient is when the capacitance is getting charged. So, what is the equivalent in terms of thermal system? In the thermal system, initially the temperature of the system is different from the temperature of the ambient, and once we communicate the two at t equal to 0, the temperature of the system or the thermometer will start going towards the temperature of the ambient, which is a constant value, and therefore, the temperature will approach it as t tends to infinity, as the time becomes large compared to the natural time constant of the system, much larger than time constant system, the two temperatures are going to be the same. So, we can say that we have equilibration of the temperatures. Equilibration of the system and the surroundings. So, let us look at the way we are going to get the solution to the problem. All I am going to do is to use the general solution here. I am going to put t infinity equal to constant. So, this I am going to replace by, this will be replaced by a constant value t infinity, and all I have to do is to obtain this integral, and then I will be able to get the solution of the problem. Let us look at that one. So, the thing I require is 0 to t integral e to the power of t by tau multiplied by t infinity dt. Because t infinity is now constant, I can take it outside and I will write it as 0 to t e to the power of t by tau dt, and this is a very simple integral. So, this becomes t infinity tau e to the power of t by tau. So, if you differentiate this, you will get, if you, because I integrated, I get this one, you differentiate this, you will get this one. And therefore, the temperature T at a function, as a function of time, is given by, of course, you have to take it with respect to only between 0 and t. So, let us just complete that. This will become t infinity multiplied by tau e to the power of t by tau is e to the power of t by tau minus 1. So, if I put it back into the general solution of the problem, so if I put it back into the general solution of the problem, t as a function of time, I have t I e to the power of minus t by tau plus e to the power of minus t by tau divided by tau multiplied by that integral. That integral is now t infinity tau into e to the power of t by tau minus 1. Okay, this tau will cancel off with this tau, and therefore, you see this e to the power of minus t by tau multiplied by e to the power of t by tau, it is going to give 1. So, it is plus t infinity here. Therefore, I will see that t by t of t minus t infinity. So, this term will go to the left hand side, this t infinity, this multiplied by this is t infinity, that will go to the left hand side, is equal to t I minus 1 into T infinity is minus T infinity e to the power of minus T by tau, or T minus T infinity divided by T I minus T infinity. I will call it as ratio of two temperature differences equal to phi, which is a non-dimensional temperature ratio, which of course is a function of time. This is equal to e to the power of minus T by tau is again a non-dimensional ratio of time in T seconds or T in whatever units to the time constant is the same unit. So, you see that this equation represents the solution to the problem. So, there is an exponential response. The advantage of writing in this particular form is that I have only one universal curve, which is going to give the reference the response of the first order system to a step input. So, let us look at the step input in the presentation. I have made a plot of whatever I showed in the solution there. The ratio of the temperatures T minus T infinity divided by T naught minus T infinity or T I minus T infinity. I have taken T I there, it does not matter. T naught here represents the initial temperature, T infinity is the temperature of the ambient, which is what we want to measure, and initially the temperature of the sensor is different from the ambient temperature. So, it will vary according to this exponential, and you see that the characteristic of this exponential variation is that at the end of one time constant T by tau equal to 1, it is about 0.367 of the value here, and if I go to another time constant, it will be 0.367 of this value, and every time constant it reduces by a factor of 1 over e. That 0.367 is nothing but 1 over e. So, you see that in principle, of course, it takes infinite number of amount of time to approach the ambient temperature, but as you can see from this graph, about 5 time constants, around the 5 time constants, the response is already almost like it has come to equilibration. So, let us look at the equation again, and what I am going to do is I am going to look at a slightly different change of temperature of the ambient. So, if I have a ramp input, ramp input is very common. For example, in when you turn on a heater, or control it to vary with respect to time in a linear fashion, used in thermal analysis of materials. Instruments which study the thermal behavior of materials usually use a programmed heating mode, in which linear or ramp input is a common feature. So, increase the temperature with respect to time in a linear fashion. Suppose I take the temperature T infinity to vary, initially it is some T naught plus R times T, where R is the ramp rate. So, if I were to plot this temperature, this is T naught and it will go like this, and the slope of this line is R, okay, linearly it is increasing with time. And now the temperature of the sensor may be either higher or lower than the T naught to start with, and we would like to know what is going to happen. So, all I have to do is to go to this general solution which we worked out in the previously, and all I need is an integral of this form 0 to t, instead of T infinity I have T naught plus R T e to the power of T pi tau dt. This can be written as two integrals, plus R times integral 0 to t e to the power of t by tau dt. This integral is similar to what we did in the case of step input, already done, like step input. Already we have seen that. Here we have an integral which involves the product of t and e to the power of t by tau. This can be done by integration by parts, and in fact I am going to leave it as an exercise for the student to work out, and I will give only the final answer to the problem. So, what I am going to do is I am going to give the final answers to this. This is already done, step input case has already been done. Instead of t naught we had in t infinity there. This integral 0 to t e to the power of t by tau dt can be integrated by parts, and it can be shown. So, this becomes, I will call this as I show that this is equal to, so I will just give the final expression t multiplied by tau e to the power of t by tau minus tau squared into e to the power of t by tau minus 1 by integration purpose. It is very simple and straightforward. So, what I am now going to do is to substitute it into the general solution and simplify and write it in this particular form. So, the solution turns out to be, I will simplify it to this particular form, t of is equal to t I minus t 0 plus r tau e to the power of minus t by tau. This is the first part plus t naught plus r t minus r tau. This is the second part. So, if you look at the first term, there is an exponential term, and as t becomes larger and larger, this is going to become smaller and smaller. So, we will call this as the transient part, we will call it the transient part, which tends to 0 as t tends to infinity, which will be interpreted as t greater than tau, t very large compared to the time constant system, and this we will call as the steady state response, wherein if you look at this, you will see that when this tends to 0, when the transient part has already become 0, the surviving part, the part which remains, is called the steady state response. It is nothing but, this is t naught plus r t is nothing but the input, that is the rate at which the ambient temperature is changing. Therefore, there is a small or a lag with respect to the input. That means that the two are going to vary alike, with a small, with a lag, the output the response of the sensor will lag behind the response of the input. The input is changing with respect to time according to a ramp input, this will be slightly lagging behind that. Therefore, it will always be behind that. Actually, we will see that if we were to look at the solution by plotting it as I am showing here. So, I am going to plot it again t by tau on the time axis, and then I am going to plot t here on the y axis. So, the input is like this, this is your input, this value is t naught, and the slope of this line is r. Suppose the initial temperature of the sensor is here, it will first try to catch up with this. So, it will vary like this and go and become parallel to this. This will be equal to r tau. If it is starting with a value higher, it will first decrease and it will go below this and then go here. Either way, this is let us say case 1, case 2 T I is here. Initially what happens? The sensor is at a higher temperature, so it cools, because the ramp is starting with a lower temperature. So, it will cool and it has to cool below the temperature of the system of this ambient, and it will cross over and then it will start increasing again, and then ultimately in this case also it will lag behind by a factor equal to r tau. Okay, this is the general behavior you are going to see, and I have made a plot for a particular case. In this slide, I have taken T infinity, which is in degrees Celsius. It is given by 35 plus 0.15 T, where T is in seconds. The time constant of the sensor I have taken as equal to 10 seconds, and I have shown the plot when the temperature of the sensor was 20 degrees to start with. Okay. So, initially you see that the temperature is increasing and it is trying to catch up with the temperature of the ambient, which itself is again increasing, and therefore, it will never catch up completely. So, as T becomes, if you remember, the time constant is 10 seconds, after about 50 seconds, if you look at here, that is 5 time constants, the difference between these two graphs, these two are going to become parallel, they are both going to be linear, but with a small difference r tau. In this case, r is equal to 0.15 and tau is equal to 10. Therefore, r tau is equal to 10 multiplied by 0.15. So, 1.5 degree difference is there. So, the difference is 1.5 degrees between the temperature of the ambient, which is changing according to a linear relationship, and the temperature indicated by the sensor. So, this is the what is going to happen in the case of a first order system whose response we have plotted for a ramp input. Okay, when the temperature of the ambient is changing linearly with respect to time, there is a lag. There is always a lag, whether it starts with a lower temperature as in this case, or a high temperature. If it were to start with a higher temperature, it will cross somewhere it will cross over. So, what is this crossover? So, because the temperature is initially the temperature is lower and the temperature of the sensor is lower than the ambient temperature, it will be heating problem. The temperature of the sensor will start increasing from T equal to 0. However, if the temperature of the sensor is more than the temperature of the ambient to start with, it will have to first cool. The temperature, it has to cool down, and it will actually cool down to a temperature lower than the temperature of the ambient at a particular time, at some time, and then it will start heating again. That is what I indicated in the on the board. So, with this, let us look at the last case I am going to consider, that is the case of sinusoidal input, or we will call it as a periodic input problem, periodic variation in temperature. There are many instances where periodic changes in temperatures are to be measured. Example, you have a electrical machine, or variation in daily temperature. For example, temperature inside an engine, inside an IC engine, inside the cylinder there is a gas, and the temperature or the wall of the IC engine will also have a periodic temperature variation. This period of the periodicity of the wave will be determined by the speed of the engine. Temperature inside the engine varies with the speed, varies as the speed. So, in the case of electric machine, if it is 50 cycles, so we expect the temperature to vary somewhere in that vicinity of 50 cycles. In the case of a IC engine, depending on the speed, the temperature will vary with respect to time. And in fact, what I will do is I will just take a simple case where I will assume it could be a pure sinusoidal or pure periodic wave given by one single frequency, or it could have a shape which is not necessarily sinusoidal. So, if it is a pure wave, pure sinusoidal, it is characterized by a single frequency. It is a more complex wave which contains, which has a shape, it have multiple frequencies. So, there may be a frequency which is we call it the fundamental, which is given by the periodicity of that wave, and there will be harmonics which are at higher frequencies. So, if you look at the solution to the problem, what I have to do is to obtain that integral which is given by integral 0 to t infinity as a function of time e to the power of t by tau dt. This is what I have to obtain. And if I assume that t infinity t is a pure sinusoidal wave or pure periodic wave with one frequency, I can take for example t amplitude T a cos omega t. I can take either cos omega t or sin omega t, it does not matter. I am just taking T a cos omega t, and T a is a constant. This is called the amplitude, and this is the circular frequency, in actually radians per second. If the frequency is f, is the frequency, then omega will be nothing but 2 pi times f, omega equal to 2 pi f. So, let me just indicate how we are going to solve this problem, and I will actually leave the details to the student to work out. So, if you look at this integral, what I want is the integral given by cos omega t multiplied by e to the power of t by tau dt. Again I will integrate it by parts. So, first integration what will happen? I will be integrating e to the power of t by tau, keeping this as such, and then I will have to differentiate this when you do the integration by parts, and the differentiation will give you a sinusoidal, because cos becomes sin. Suppose I repeat again, afterwards I will get an integral which involves sin, and I will repeat, and then second time I integrate, I will get back the cos omega t. That means that if I integrate first once by parts, I will get the integral will change over to from cosine to sine, and then I integrate second time, the sine will become again cosine. Therefore, the integral will repeat itself. Okay? And to conserve time, I will not indicate the steps involved. I will just give the final answer to the problem. Those who are interested can work it out on their own. So, the integral repeats after two integrations. This is the observation we are making. So, mathematically we can look at it, but we are not inclined to do that. So, the solution can be written as T I minus T A divided by 1 plus omega squared tau squared whole multiplied by e to the power of minus t by tau. We will call this as the transient part, just like what we had in the case of a ramp input. The solution is made up of two parts, the transient part plus again we have what is called a steady state response part, which is given by T A multiplied by cosine omega t minus delta, which is called the phase angle, divided by square root of 1 plus omega squared tau squared. This solution can be worked out by the method I have suggested. So, again transient part tends to 0 as t tends to infinity, which means t something greater than about 5 tau, let us say. So, what will happen is, as the temperature, as the time becomes larger and larger, the response is given by the second part. This is called the steady state response. And what we notice from the steady state response is that it is also cosinusoidal, but it is omega t minus delta. That means, there is going to have a lag with respect to the input, and in fact delta is given by tan inverse of omega tau. Okay. And the coefficient is T A divided by square root of 1 plus omega squared tau squared, and omega tau 1 plus omega, this is smaller than T A by a factor greater than 1. Therefore, the amplitude is reduced. Therefore, we say that there is an amplitude reduction. So, T A divided by square root of 1 plus omega squared tau squared, and delta is equal to tan inverse omega tau. And in fact, I have worked out a simple example to show what is going to happen in the case of a response to a cosine input, as we said. So, I have taken a specific case T A by T naught equal to 0.25, omega equal to 1 radian per second, and tau equal to 1 second, and you see that the temperature, it starts, this is the input which varies like this, and the response of the system is following the other curve, and you see that it's initially there is a transient, it dies down, then both of them become periodic, there is a time lag as shown here, and the amplitude is smaller than the other amplitude by a certain factor. So, what I will do is, in the next lecture, I will just briefly touch upon this case again and indicate what happens when you have a general periodic input, which may not be a pure sinusoidal, and we will look at that case, and then what I am going to do is to look at other methods of measurement of temperature using different types of sensors. Thank you.